Hello everyone, I'm Hanlin from the University of Oxford. Today I'm going to talk about my joint work with Duan from Tsinghua University on maintaining exact distances under multiple edge values. So the problem is very easy to state. Given a graph, you want to deal with values. In each query, you are given vertices u, v, and a set of values d. You want to find the shortest path from u to v that avoids d. Here's an example. You have this input graph which you need to preprocess. Then on each query, you are given a set of failed edges, and you want to find the shortest path from the source vertex to the target vertex that does not go through the failures. So what is known about this problem? The easiest case is when you only have one failure. Now the query becomes like you are given vertices u and v and a failure f, where f is either a failed edge or a failed vertex. You want to find the shortest path from u to v that avoids f. This problem was studied extensively, and there's a long line of work on this problem. They accumulate to highly non-trivial solutions with size tilde O n square and query time constant. Both parameters are optimal for this problem. So when we have two values, the problem becomes considerably more complicated. This was studied by Duan and Petty in their 2009 paper. They achieved space complexity tilde n square and query time log n. This is also quite close to optimal. But one problem with the Oracle is they used very heavy case analysis, and the structure of shortest path under two fields looks really complicated. So their techniques do not seem to even extend to three failures, and because they used very heavy case analysis, they even suggest that moving beyond dual failures would require a fundamentally different approach. So what about more failures? When we have D failures where D is a large constant, previous work can be categorized into two types. The first type is when you only want to answer weaker queries than exact distances. For example, you only want to know the connectivity or approximate distance between two vertices after a failure. Then, in this case, you can achieve a query time polynomial in log n and d, which is considered fast. The second type is when you insist on maintaining exact distances. In this case, previous work can only achieve query time polynomial in n, which is considered slow. So in this sense, exact distances seem to be much harder than approximate distances. But in this work, let's focus on exact distances. So you are given d failures. You want to maintain the exact distance between two vertices. The naive solution is to just construct a lookup table. You enumerate all possible queries, and you build a lookup table for all possible queries. The size is O n to d plus 2, and query time is constant, because there are n to d plus 2 possible queries. Duan and Petty observed that the dual failure oracle can be used to achieve size tilde O n to d and query time O log n. Basically, you enumerate the d minus 2 failures, and then for each such d minus 2 failures, you remove them from the graph and you build a dual failure oracle in the rest graph. You use the dual failure oracle to deal with the rest 2 failures. So the total size is n to d minus 2 times n squared, which is n to d, and query time is O log n. These are the only results with fast query time. Here by fast query time, I mean if d is a constant, we want the query time to be polylog in n. So we don't know for a large constant d if there is a d failure exact distance oracle with query time polylog n and a reasonable size bound. Here, reasonable size bound means the size is n to c, where c is some constant independent from d. Let's say the size is n to 10th, even if we have d equal to 100 failures. Actually, even the answer to the following easier problem was unknown before our work. Let's say d is 100. is there a d-value exact distance oracle with period time polygon and size like n to 99, just slightly beating the n to d bound. So what are our results? We show that the answers to the above two problems are yes, at least for undirected graphs and edge values. Our main result is uh, an exact distance oracle under d edge values with current time d2od and size d times n fourth. The precise statement is as follows: let G be an undirected weighted graph. For every constant d, there is an oracle that handles exact distance queries in G under d edge values. The oracle has size n2 fourth and query time constant. Here d is a constant, so we also treat d2od as constant. So now let me introduce some techniques. First, we need the following structural theorem about shortest path under d edge values. F(x) proves that any shortest path under d edge values can be decomposed into the concatenation of at most d plus 1 shortest paths in the original graph interleaved with at most d edges. Here's an example when d is equal to 3. So the long path is a shortest path under 3 edge values. By the structural theorem, it can be decomposed into the concatenation of 4 shortest paths interleaved with 3 edges, where each shortest path is the shortest path in the original graph. So this suggests a recursive approach. But to state the recursive approach, let me start with some definitions. Path G minus d uv is the shortest path from u to v after d fails. Rank G minus d uv is the number of segments in path G minus d uv. More precisely, it's the minimum number of segments we can partition path G minus d uv into, such that the structural theorem holds. Here each segment just means a shortest path in the original value-free graph. So the structural theorem states that for every uv and every set of d edge values, rank G minus d uv is at most d plus 1. Our goal in the recursive approach is to find some vertex W that is on path G minus d uv, but neither on the first nor on the last segment. So, for example, this green vertex is okay because it is indeed on the path G minus d uv, but it's neither on the first nor on the last segment of path G minus d uv. This green vertex is also okay. This red vertex is bad because it's on the first segment. This red vertex is bad because it's on the last segment. Finally, this red vertex is bad because it's not on the path G minus d uv. So why are such W useful? If we have such W, then rank G minus d uw and rank G minus d wv are strictly smaller than rank G minus d uv. Actually, since W is not on the last segment, we can see rank G minus d uw is strictly less than rank G minus d uv. Also, since W is not on the first segment, we can see rank G minus d wv is also strictly smaller than rank G minus d uv. So we can recurse on uw and wv, then concatenate the two paths we found. The recursion depth should be only d plus 1 because rank decreases by at least 1 at each level. Now, here is a slightly more formal description of our recursive query algorithm. So UVD. The base case is when rank G minus DUV is 1. This means that the original shortest path from U to V does not contain failures, so we can simply return this path. Otherwise, we find some W that is on path G minus DUV and neither on the first nor on the last segment. Actually, we don't know how to find the one single W. We only know how to find a hidden set of poly D vertices such that one of the vertices satisfy the above two conditions. So what we will find is actually a set of poly D vertices, most of which are maybe useless, but one of the vertex W satisfies these two conditions. So we can then enumerate the vertices in this set. For a vertex W, we concatenate solve UWD and solve WVD, and we return the shortest path we found. The recursion depth is OD. And each non-leaf node in the recursion tree has poly D children, so the recursion tree has size D to OD, and the time complexity is also upper bounded by D to OD. So what remains to do is to show how to find such a heating set. We want to find a heating set of poly D vertices, one of which is on the path G minus UV, but it's neither on the first or nor on the last segment. As our time is limited in this talk, we will only do two things. First, we will ignore the second condition, but only find a small heating set that contains some vertex W in path G minus UV. So W might be on the first or on the last segment. We just want to find a heating set of poly D vertices that hits this path. This is actually very simple, and I'll do it in one slide. Second, we give you some taste of our techniques on how to escape from the first or last segments. So suppose our vertex W found is on the first segment. How do we escape from the first segment and find something not on the first segment? This turns out to be the most technical part of our work, but I still want to highlight some ideas in the later slide. Okay, so let's first consider finding a heating set of the path, ignoring whether the vertex is on the first or last segment. The solution is quite simple. Define d star UV be the maximizer of this G minus DUV, that is, the set of d edges whose value maximizes the distance from U to V. We claim that d star UV is a good heating set. The proof is also simple. Suppose d star UV is not a good heating set. Then there's some value set d such that path G minus DUV does not go through d star. So if we remove d star from the graph G, then path G minus DUV still survives from these values. So it's a valid candidate for this G minus d star UV. This would mean that the length of this path is at least this G minus d star UV, because this distance is optimal. So this means that this G minus d UV is at least this G minus d star UV. But notice that d star maximizes this quantity, so the inequality is actually an equality. In our Curie algorithm, we are given UV and D. So we have two cases. Either this G minus DUV is equal to this G minus D star UV, or D star UV is a good heating set. If the first case happens, then this is actually trivial, at least if we only consider distance is not passed. And in the second case, D star UV is a good heating set, so we can do recursion. Good. And now I'll give you some taste of how we escape from the first or last segment. Let's consider the following scenario. We already know vertices U prime and V prime on the first or last segment respectively. These vertices represent our failure to find vertices not on the first or last segment. So recall that we find some vertex W in the heating set. And if W is not on the first or last segment, then we are done. But if W is on the first or last segment, then let's say it's on the first segment, then we set U prime to be W, and we will need to fly away from the first segment somehow. Let D star UV U prime B prime be the maximizer of this G minus DUV, where this D does not intersect path U prime and path V prime V. Since the actual set of values do not intersect path U to U prime and path V prime to V, we know that D star is a good heating set for this path from U to V. We know that D star is a good heating set for path G minus UV. So we can find some heating vertex W from D star. If W is not on the first or last segment, then we are done. Otherwise, let's say W is on the first segment, we will need to push U prime to W. So the problem is how many times do we need to push down U prime? The trivial upper bound is On, so U prime and W might be very, very close to each other, and we are not really making progress. Here is our idea. First, some notations. Let Tu be the shortest path tree rooted at U, and Tu U prime be the subtree of Tu rooted at U prime. Now let U LCA be the lowest common ancestor of the values in Tu U prime. So in this case, U LCA is the green vertex. It's the lowest common ancestor of these three values. Instead of du v u prime v prime, we consider d star u v u LCA v LCA, which is the maximizer of this G minus duv, where d does not intersect path u LCA and path v LCA v. Note that there are no values, there are no actual values in the path from u to u LCA, so it's valid to consider this d star. And then when we find a hitting vertex in D star, we push down U prime to this hitting vertex. Consider the question again. How many times do we need to push down U prime? Each time we push U prime to some vertex that is strictly below U LCA. So let phi U prime be the number of values in TU U prime. Then phi U prime is at most D, and each push down strictly decreases phi U prime, because you push down U prime to some vertex that is strictly below U LCA. So we only need to push down D times. This is good. After some calculation, this gives you a hitting set of size polynomial in D. The space complexity of our data structure is ODn4 because we need to store D star UV U prime V prime for every quadruple UV U prime V prime. So in conclusion, we present the first exact distance oracles that support multiple edge values with a reasonable size bound n4 and fast query time constant. There are some obvious open questions. The first open question is whether we can support vertex values. The structural lemma doesn't work for vertex values, but as far as I know, all of our other techniques should work for vertex values. Another open question is whether we can achieve faster preprocessing time. The bottleneck of preprocessing is to compute D star UV and D star UV U prime V prime. I don't know how to do that in less than n-d time. Perhaps we need to find a good approximation of D star UV and compute it faster. Finally, can we improve the size bound to n square? Currently it's n4. So the data structure is not optimal for like 3 or 4 failures. And that's all. Thank you.